Hello everyone, today in this video we'll be discussing about the topic lasers and optical fibers. This is the first topic in the module 1 of physics. So before getting started, let me tell you, in this video we'll be discussing about the important questions from these two topics and how do you remember the diagrams and what are the key points in each of these topics. If you watch this video till the end, it will be sufficient for you to score more than 80% marks in the exam. So without wasting any more time, let's get started. Make sure you hit the like button, subscribe to my channel for more videos like this. Now let's get started. So module 1 of physics is comprised of two things. First is laser and second is optical fiber. Okay. So lasers we all have played. It's a device which emits a very strong light. Okay. It travels to a very far distances. So we will be learning about what is laser and how it works. Okay. So it's a very interesting topic. There are 5 topics which you need to know from the exam point of view. So what is a laser? Laser stands for light amplification by stimulated emission of radiation. Okay. So what's happening is we have a laser and the light is coming out of it. Okay. So what is this light? This light is nothing but photons. Okay. It's called as photons. Now how do photons get emitted? Photons get emitted when electrons come from higher energy level to lower energy level. Okay. When electrons jump from excited state to lower state, at that time photons are emitted. Okay, that's how the laser light is coming. So we have 3 types in the radiation. The radiation is of 3 types, which is the first is the induced absorption, and the two are spontaneous emission and stimulated emission. Okay, so what is absorption? Absorption means getting something into it. Okay, absorbing it. Emission means getting something out of it. Okay, so what is induced absorption? So before discussing about absorption and emission, let's discuss what causes the photon to emit. Okay. So suppose that there is an electron E here, which is in the higher state, and this is the lower state. Okay. So when the electron comes from higher state to lower state, there is an energy difference. Okay. So if this is E2, higher state is E2, and lower state is E1. If the electron jumps from E2 to E1, that is called as energy difference, and at that time the photon will be released. And photon is nothing but light. Okay, it is nothing but light. Okay, so this is the main concept on which the lasers work. And according to Max Planck, energy is equal to h into nu, which is the frequency. Okay, and E2 minus E1 is the equivalent of h into nu. So h nu is equal to E2 minus E1. Okay, this is an important formula we'll be using in this module. Okay. So there are 3 types of radiation which we are going to discuss. The first is the induced absorption. So what happens in induced absorption? There is a E2 energy level here, there is an E1 energy level here, and a photon is going here. Okay, a photon is traveling this path. So what happens is this photon gets absorbed by this energy level. Okay, this photon gets absorbed by this energy level. So what happens is the electron which absorbs the photon, that will go to an excited state in the E2, which is in the higher level. Okay, so this is the before scenario, this is the after scenario, and the equation can be represented as atom plus photon is equal to atom star. Okay, so this is the normal atom, and when photon is absorbed inside it, so it will become an excited atom, which is denoted as a star at the top of it. Okay, that is the induced absorption. Now the opposite is the emission. Now we have 2 types of emission. The first is the spontaneous emission, second is the stimulated emission. Okay, spontaneous emission directly opposite of the induced absorption. Here we have an E2 energy level, and the electron comes from the higher state to the lower state. At that time a photon gets emitted. Okay, this is how the laser light comes, when the electron from higher energy comes to the lower energy. The equivalent equation will be atom star, which is the excited state, that can be represented as an atom which is in the lower state plus a photon which is getting emitted here. That is called as spontaneous emission. The last one we have is the stimulated emission. In stimulated emission, both of the things happen. The first thing is the electron comes from a higher state to a lower state. The second thing is a photon gets emitted. Also it will have an initial photon present. Okay, so this is an initial photon which causes it to come from a higher state to lower state, and since it came from higher state to lower state, there was an energy difference, so another photon got emitted. Okay, so these are the 3 types of interaction of the radiation: induced absorption, spontaneous emission, and stimulated emission. A very important concept from exam point of view. Okay, and E2 minus E1 is equal to h nu, and this can be represented as atom star, which is the initial excited atom, plus photon, this is the photon. When these two occur together, what happens is an atom is there which is in the lower state, and extra photon gets released, which is 2 photons at the end. Okay, so that was our first topic. Moving on to the second topic, we have expression for energy density. Okay, so here we have a derivation which is very important from exam point of view. Okay, so before moving on to the derivation, we have to first understand few key concepts. Okay, so here we are assuming that there are two energy levels, E1 and E2. Okay, so E2 is a higher energy level and E1 is a lower energy level. Okay, these two energy levels are present, and the population levels at N2 at E2 and N1 at E1 means how many electrons are present in E2 level, that is in the N2, and how many electrons are present in the E1 level, that is N1. Okay, and energy density is represented as UV and frequency is represented as nu. Okay, now here we will be using the Einstein coefficients of A and B. So what is Einstein coefficient? Let's understand. So we have discussed three things. Okay, one is the absorption and two are the emissions. So absorption is induced absorption and the emission is spontaneous emission and simultaneous emission. Okay, we'll be using both of these in this derivation. Okay, so what is induced absorption? Induced absorption is rate of absorption. Okay, that is equal to N1 into UV, and B12 is the proportionality constant, because the absorption happens with respect to how much energy density is there and how much the population is there. This is the population, this is the density. If it is more, there are more electrons and there is more density is there, that will increase the rate of absorption. Okay, so remove the proportionality constant, we'll be using this one, B12. Okay, so to remove this one from to equal to, we'll be using B12. So B12 is the proportionality constant of induced absorption. Okay, similarly for the spontaneous emission also we have the same. The rate of spontaneous emission is equal to A21 into N2. Okay, so A21 is the proportionality constant, and spontaneous emission is independent of the density. Here we have used the density, right? So it is independent of it. Okay, here only we'll have A21 and N2. The third one is the stimulated emission. So the rate of stimulated emission is equal to B21 N2 into UV. Okay, so it is proportional to N2 into UV, and to remove the proportionality we'll be using a constant B21. Okay, so this is the constant we are using, B21. So let's summarize. We have three formulas. The first is the induced absorption, B12 into N1 into UV, spontaneous emission A21 into N2, and stimulated emission B21 N2 into UV. Okay, the first step, you are required to memorize this one. It's very simple. If you glance it two or three times, you will be getting to know the formulas. Okay, so once you have memorized this formula, we have to write an equation. So the equation is very simple. Rate of absorption is equal to rate of emission. Okay, so absorption is equal to two emission types, spontaneous and stimulated. All you have to do is, this is equal to this plus this, you have to write it in this way. Okay, so B12 N1 UV is equal to A21 N2 plus B21 N2 UV. Okay, now we are rearranging, very simple. We are taking the UV out from here and here, and we are keeping this in the same place. We are transferring this here, so we will be obtaining UV into B12 N1 from here and B21 into N2 from here. Okay, that is equal to A21 N2. Now keeping the UV here, transferring this term into the denominator, we will be obtaining this equation. Now what we are doing, we are taking N2 as the common. Okay, so when we take N2 as common, here what will happen, this will become sorry, we are not taking N2 as common. What we are taking as common is B21. Okay, means we are dividing this is as B21, and here also we are dividing it as B21. Okay, so when we do that, and also we take it separately, so what happens is we'll be cancelling this one. Okay, this I'll explain in depth. Just give me 1 second. Okay, so here what happened is, see, A21 and B21 is here. Okay, so A21 and B21. Okay, so we multiplied and divided by B21. Okay, initial equation was this one, right? B12 N1 minus B21 N2. Okay, this was the initial equation, and we had A21 and 2. Okay, so B21 was not there, right? So let me erase this one. So okay, This is the first equation which we had. Okay, this is equivalent to this, right? Now what we are going to do, now we are multiplying b21 and dividing b21. Okay, so when we do that, the division will be going here, right? You can get to know this. The division denominator will be going here. So what will happen? Let me move it to here. It will be here b21, and here also it will come b21. Okay, now these two will get cancelled, and what will remain is b12 by b21 into n1 minus n2. Okay, that's what it is written here, and b21 will be present here. Okay, so this is how you will be getting the uv formula. Okay, so after this one you have to do a few more things. Next, we'll be doing a similar thing here with n2 as well. So here we have n2 in the numerator, right? So what we will do, we will multiply this term, okay, with n2. Okay, so what this term will become? b12 by b21 into n1 into n2 by n2. Okay, it will become into n2 divided by n2. Okay, so and when we take the numerator n2 outside, this will become 1, and this will also become 1. Okay, that's what happened here. Okay, here it is 1, and here it will be n1 by n2. Okay, so let me elaborate this how this happens. Okay, so I have written the term here n1, and when we are multiplying by n2 and dividing by n2. Okay, and it is minus n2 here. Okay, so when we take n2 as common, what this will become? This will become b12 by b21 n1 by n2. We are taking the numerator, right? So it will be minus 1, and n2 will be here. Okay, this is what the equivalent of this one, right? And here also n2 is there at the top, so from the top and bottom it will get cancelled. Okay, from the top and bottom it will get cancelled. All right, so this is how we obtain this equation. Okay, next what we are going to do is we are going to take the Boltzmann's law. Okay, till here you just have to remember one thing. Just get these three equations. Okay, substitute it, and rearrange the terms. After rearranging, you will be getting the uv value. Just take b1 to b21 out, and n2 out. Okay, so you'll be arriving at an equation similar to this one. Okay, after that your second step is to take the Boltzmann law. Okay, so what does the Boltzmann law say? By Boltzmann law, we have n2 is equal to n1 into e power minus e2 minus e1 divided by kt. Okay, that is equivalent of n1 into e power minus hv divided by kt, because hv is equal to e2 minus e1, so it will be minus hv by kt. Okay, so rearranging the term n1 here, we will be getting n1 by n2 is equal to e hv by kt. Now we will be using this one and substituting in the uv equation. So where can we substitute n1 by n2? We can substitute it in this place. Okay, so when we substitute that, we will be obtaining the equation as follows. Okay, we'll be obtaining the equation as follows. It will become e power minus hv by kt. Just in the place of this one, we are substituting e power hv by kt. Now this is the new uv. Okay, you have to remember this one. Our third step and the last step is to use the Planck's law. So what is the Planck law? Planck law says uv is equal to 8 pi hv square divided by c cube. V cube divided by c cube, and multiplied by 1 by e power hv by kt minus 1. Okay, so since uv is equal to this and uv is equal to this, so we can compare these both as equal. Okay, so when we compare both of them, what we get is a21 by b21 is equal to 8 pi hv cube by c cube. These both are equal, and this term and this term is present here, so this term is equivalent to 1, because 1 is multiplying with this one, so only we don't have anything here, right? So b21 by b12 by b21 is equal to 1. So these are the two observations we have got. Okay, so this is the first observation, and this is the second observation. Since b12 by b21 is equal to 1, that means b12 is equal to b21. Both the coefficients in the emission as well as the absorption both are same. Okay, and A will be remaining like this only. Since B12 and 21 both are same, we will be denoting it as B, and this one A will be denoting it as A. Okay. So substituting both of these in the our main equation, we will be obtaining UV is equal to A by B into 1 by E HV by KT minus 1. Okay. So this is the equation which you need to derive for the energy density using the Einstein's coefficients. Okay. So this is a very important question. Please write 3 times in practice so that you can remember it in your mind. Okay. So our third topic is related with a few important concepts which are repeated a lot of time in exams. So what are those topics? Very simple topics. What are the conditions for laser action? Okay, when does laser action happen? So there is a condition of two things. Okay, one is that there should be a metastable state. What is metastable state? A state in which the electron stays stable for more than normal time. Okay, that is what is called metastable state. Population inversion means in the higher level there should be more electrons than the lower level. Okay, what is population inversion? In the higher level there should be more electrons than in the lower level. Okay, when these conditions are not present, laser action cannot be possible. Okay, so that are the conditions for laser action. Next we have what are the requisites of a laser system. That means um, to ensure that the laser action is happening, what is the requisites means the environment, how it should be, and what should be the electrons present, and those things. Okay, it's similar to the condition but slightly different. So the requisites are two. Pumping process means we have to push the electrons into a higher level. That can be done optically by using light, or we can do it using electrical waves. Okay, that is the pumping process. We have to have electrons more in the higher level. Why? Because we need to have the population inversion, right? So for that we need to pump the electrons to the higher level. And active medium should be there, which is the laser cavity. This means that it should be a environment which is supporting the laser activity. Okay, so this is a special environment which is having some properties which supports the light of laser to travel smoothly. Okay, so here we have the reflector and the reflector, and here we have the output beam. Here we have the amplifying medium to make the laser more darker. Okay, now moving on to the fourth topic, which is building the laser. Since we have got to know a lot of about the laser, let's see how the lasers are built. Okay, it's very easy. We are discussing about the gallium arsenide laser. Both are semiconductors. We'll be using gallium arsenide laser to understand how it is made. Okay, so this is the diagram. What all you can see in this diagram? There are few main things. The first thing is there is a circuit here. Okay, easily you can draw. Then draw a cuboid here with the p type at the top and n type at the bottom, and in between we have a laser beam emitting out of it. Okay, and that is the active region. Got to know? We have a circuit here, and we have the n type and p type present here. P type first, then n type, and then we have the laser beam emitting out of the active region. Okay, so how does it work? Okay, so let me show you how does it work. To generate the laser beam, the population inversion is required. That means at a higher level, more electrons are required than at the lower level. Okay, so how do we achieve that? The below diagram shows the initial environment before the laser. Okay, so before the laser, how it looks like, the p type and n type. Okay, let's zoom a bit into this part. Okay, so if we zoom a bit into this part, we'll be having the junction here. The middle part is called as junction, and this is the n type and this is the p type. Okay, this is at the bottom and this is the top. Okay, and we have different kinds of energy levels present here. Okay, so what's happening is the shaded part is the part where the electrons are present initially. Now what we have to do, we have to modify the junction. Okay, here we have to do some modification. So when we do the modification, the electrons will come from higher level to the lower level. Okay, means we just have to do the population inversion first by using some other method, which is the electrical signals will be sending from here. So what happens, the electrons will be coming here and the holes will be generated here. After that, electrons will be jumping to the holes, and what will happen, the photons will be released. Okay, so to achieve population inversion, the junction is modified. How it is modified? By using biasing. Okay, we'll be using the forced bias by sending the electrical signals so that electrons come here in the higher level. This is the inversion region. this is the higher level, and the holes generate here. So when electrons come here, the opposite of it happens at the lower level. This is holes. Okay, what happens then? This will come to fill the holes here, and the electron will be the photons will be released. This is nothing but the laser. Okay, this is how the laser comes out of the picture I had shown you, right? Yeah, this is how the laser comes. Okay, so n type is the higher level, p type is the lower level. From n type into p type it is jumping, and then it is releasing the laser. Okay, and the initial bias which I told you, that is provided by this one. Okay, it will give some initial bias for the electrons to populate at n type, then it will jump to p type, it will release the laser from here. Okay, all right. So that was about the working of the gallium arsenide laser. Let's have a look at the last topic, which is applications of laser. So where all do you think the lasers will be used? The first thing which comes in our mind is that we had played with lasers. It's a very fun thing to play with, but there are a few other places also in the real life where we'll be using. So let me share with you the applications of the laser barcode reading. Okay, so when we go to the market and purchase something, we will be seeing the scanner here, right? It will be scanning the barcode. How does it work? Okay, so there is a mirror attached here, and the laser photo detector is present here, and the laser will be given from here. So laser will hit all of these spots, and it will reflect back by using the mirror. Okay, now what will happen? Where there is black spot, right, it will get absorbed and not reflect. Okay, black spots it will not reflect, the remaining spots it will reflect. So it will get an idea of how many positives are there, how many negatives are there, means which are higher level, which are lower level. So bar and space, this data we will get, and this data can be converted to our code, so that we'll get to know with ones and zeros what is the code of that product. Okay, so this is the application where the laser is used. The second application is in the laser printing. Okay, so what is laser printing? Laser normal printing, we know we'll be having an ink, we'll be putting into in the computer system, and printer will use that ink to print at that point where we want to get it printed. Okay, and then a paper will come out. But in laser printing, something different will happen. We'll be having a kind of tube here. Okay, cylindrical tube, and the laser will be pointed to the points where the printing should happen. So whenever a laser is pointed like this, at that point the properties of it will be getting altered. Okay, so what will happen if properties are altered? It will be able to produce the ink. Okay, so when the ink is produced, there will be a tube where the ink is present, and the laser will activate that link, and on those spots the printing will happen, and this is the paper where the printing will happen. Okay, so this is how the uh, laser printing happens. It's happening in the following steps: image processing, first providing data to the laser, which points you have to point to. Okay, and then charging, which means warming the paper for the printing, and exposing, exposure will happen to here, developing, where all it's needed to be developed, the laser will be pointing to that locations, transferring this ink to the paper, and then fusing means the ink will be finalized on the paper, and then it will be printed. Okay, this is how the laser printing works. The last application is the laser cooling. Okay, what do you mean by laser cooling? So to make something cooler, we'll be using the laser. Okay, so what we are making cool here, we are making the electron cooler, electron or the atoms cooler. How do we do that? So it's very simple. So what happens when we point a laser? When you point a laser, at that time the electron from the higher level comes to the lower level. That means it will travel some distance. So when it will travel some distance, it will become tired. Okay, tired means there will be loss of kinetic energy. When there is loss of kinetic energy, there will be heat loss. So ultimately, what does that mean? If there is a heat loss, that means the temperature of the atom is reduced from a higher to a lower point. That's what the laser cooling is. We'll be using the laser to cool down the atoms, so that the entire object will be cooled. Okay, so that was about the first half of the module, which is the laser. Similarly, we have another topic, which is the second half, optical fibers. Okay, so in optical fibers we have four topics. Okay, what is optical fiber? We have tube kind of wire like this. Okay, so this is the optical fiber. What does it do? It will transfer the data. How does it transfer the data? It has the built-in structure like this, wherein the light will be transferred. Okay, how does the light transfer from here? We'll be discussing in depth. So that is what is an optical fiber. It will transfer the data in the form of light. Okay, here also one derivation is there. numerical aperture and acceptance angle. We'll be discussing how do you remember that one. Okay, it transmits the data in the form of light, and it works on the principle of TIR. What is TIR? Total internal reflection. This is a very important concept, without which the optical fiber won't work. Okay, what is total internal reflection? First, tell me what is reflection. Okay, suppose I put a light here. If this is a mirror, it will get reflected. This is called as reflection. Okay, so what is total internal reflection? Now let's have a look at the diagram where the reflection is happening at this level. Okay, so here three rays are there. Which are the three rays coming? A ray, B ray, and C ray. Okay, and this is the plane which is to be reflected or pass through it. Okay, based on the angle. Okay, so as you can see, A angle is theta 1, B's angle is theta C, and C's angle is so C's angle is not given here, so it is more than theta C. Okay, that's what we can infer from this diagram. So what's happening is, if it is incident at O at this angle, what will happen? It will pass through it. Okay, it will pass through it. If it is incident at this angle, which is theta C, also known as critical angle, it will get passed like this onto the plane. Okay, not any other angle, onto the plane it will get passed. And theta C, for the C, if it is more than the theta C, it will get reflected back. Okay, it is coming, see, it is like this, it will come and bounce like this. Okay, um, come and bounce like this. Okay, this is how the total internal reflection works. And for the total internal reflection to work, there should be a difference in the refractive index. Okay, what is refractive index? Hardness or the softness optically. Okay, so if there is water and air, which is having lower refractive index? Air is having lower and water is having more. Okay, I hope so you got to know. And which is having more, glass or water? Okay, more is glass, right? Because it's more harder optically, so it is having more refractive index. So for total internal reflection to occur, the n1 should be lesser and n2 should be greater. So you can assume this as water or glass, and this one as air. Okay, so this is the diagram which you need to remember. Now using the diagram, we have the derivation from the Snell's law. What does Snell's law say? N1, which is the refractive index of the medium one, into sine theta 1. The theta 1 is the angle at which it's coming, right? So see, this is the angle at which it is coming, theta 1, and which is this refractive index? N1. This is N1. So N1 into sine theta 1 is equal to N2 into sine theta 2. The reflected ray, the theta, what it is? Theta 2. So it will be N1 sine theta 1 into N2 sine theta 2. Those both will be equal. Okay. So here we are considering theta 1 as theta C, which is the critical angle. So what is critical angle? The critical angle is the minimum angle needed for total internal reflection. Okay, so as you can see here, theta 1 is the perfect angle present here on which the total internal reflection is happening, right? So theta C we are considering as the incident angle, should be theta C, and the reflection is happening here at 90 degrees. See, this is 90 degree here. Okay, so sine theta 2 will become 90 degree and theta 1 will become theta C. Okay, now what happens after substituting those values? Theta 2 is 90, so sine 90 is what? 1. So this will become 1, and this will become sine theta C. So sine theta C is equal to n2 into 1. Okay, this will become sine theta C is equal to n2 into 1, which is nothing but if we just consider theta C, transfer n1 to the bottom, n2 by n1, and take the inverse of sine here, so it will be sine inverse of n2 by n1. Got it? This is the critical angle, that is equivalent to sine inverse of n2 by n1. Okay, that is about the basic. How do we derive what is the theta C? Okay, but this is not the derivation which will be asked in exam. This will be used in the other derivation. Okay, so how does light propagate? It is very simple. Since you got to know about the total internal reflection, now we are just making a tube here, very big tube, in which multiple internal reflection will happen and the light will pass. Okay, so that's what, it's very simple. Here we have the light ray, and here we have the core. The inside part is called as core. The outer part which you see as shaded here, that is called as cladding, and the light ray will come from here. This is the pipe, and here we have the light ray coming, total internal reflection multiple times, and it will come out from here. Okay, so there is core and cladding. So now we'll be using these concepts to understand how the numerical acceptance is derived. Okay, acceptance angle. This is numerical aperture. Okay, so let's have a look at it. Okay, so this is a more detailed diagram. The optical fiber diagram which I initially showed you, it was like this, right? So it has three sections. This is the outer part, which is also might be insulated many times, and this is the cladding part, cladding, and this is the core part. Okay, so here what you have A here. A light is coming from here, incident at O at an angle of theta naught. Okay, and it is passing through here, and this angle is theta 1, and this angle is 90 minus theta 1. Okay, and it is passing through this point here. Okay, so the minimum angle it should have is this one, theta naught. That is the critical angle. Now lesser than this, if it have, then only total internal reflection will happen. Okay, so theta naught should be lesser than theta c for total internal reflection to happen. Okay, this you have to remember. Okay, so acceptance angle is what? It is the maximum angle at which total internal reflection will take place. Okay, so this is the maximum angle. If it's a bit more also, like suppose light came from here, this is the angle, then it will not happen as the total internal reflection. It will pass and absorb. Okay, it will go inside this one. Okay, for the internal reflection to happen, this should be reduced. Okay, like this light will come here like this, it will come and go like this. Okay, you got my point. Okay, so maximum angle is this one, and lesser than this will be accepted for total internal reflection. Okay, theta naught is the acceptance angle for TIR. Total internal reflection must be greater than the theta naught. Okay, so this diagram I have taken again below for the derivation purpose. Now at 2 points we have to consider the Snell's law. Okay, first is the A point and second is the B point. Okay, 2 points will be considering the Snell's law. So what is N naught? N naught is the refractive index of the air. This is air, and this is the cladding, which is N2, and this is the core, which is N1. Okay, so at this point we are considering this one. So it will be N naught into sin theta naught is equal to N1 into sin theta 1. It has inserted here, so this is theta 1 and this is N1, so it will be N1 into sin theta 1. So sin theta naught, if we take this below, we'll be getting N naught N1 by N naught into sin theta 1. This is the equation 1. We'll be using it later on. Same thing we'll do at B also. So at B it will be N1 into sin 90 minus theta 1. So this is the angle 90 minus theta 1 into N1, that is equal to, here what happened, here it is 90 degree and the um, medium is N2. So it is passing in the cladding. Okay, so it is N2. So sin 90 minus theta 1 into N1 is equal to N2 into sin 90. Okay, so what is sin 90? And 1, so it will be N2 here. Okay, N1 cos theta 1 is equal to N2. Now cos theta 1 will become N2 by N1. Now we'll be using this equation and substituting it in the first equation. How do we substitute that? Sin theta 1 is present here, right? How do we convert sin to cos? Simple. What we do? Square root of 1 minus cos theta square. Okay, this will substitute in the place of sin theta 1. Okay, so that's what we have done here. Here we have sin theta naught, the same thing which is written here, n1 by n naught, n1 by sorry, this is n naught. Okay, just remember this is n naught, and this is 1 minus cos theta 1. Okay, so cos theta 1 is what? N2 by n1. Okay, so we'll substitute n2 by n1 in this place. So what this will become? Sin theta naught is equal to n1 by n naught. Okay, this is n naught, sorry, and here we'll be having 1 minus cos theta 1 will be written as n2 by n1, so it will be n2 by n1. Simplifying it, very simple math, what we'll be obtaining is the square root of n1 square minus n2 square divided by n1 square. So n1 square will be taken as the root, so it will become n1. Here also n1 is there, this both will get cancelled, so it will be n1 square minus n2 square divided by n naught. Got my point? Okay, so this is the value of the sin theta naught. Okay, and n naught is equal to 1. Why is n naught 1? N naught is 1 because the outside medium is air and the refractive index of air, as you know, it is 1. So sin theta naught will become, this will become 1, so it will be n1 minus n2, n1 square minus n2 square root. Okay, numerical aperture is equal to sin theta naught is equal to n1 square minus n2 square. So whichever angle satisfies this condition, that will be the acceptance angle. Okay, and it should be less than this value. Okay, this angle theta naught, for total internal reflection to happen, it should be less than root, that one, n1 square minus n2 square. Okay, it should be less than that. When theta is equal to less than theta naught, then only propagation can take place. Okay, so the angle should be lower than the acceptance angle. Okay, acceptance angle is the maximum angle. Okay, below that total interreflection will happen. Okay, so it can also be written as sin theta I is equal to less than sin theta naught, or less than na, or less than square root of n1 square minus n2 square. Two concepts of the theory: fractional index change, that is the ratio of the difference in the refractive index of core and cladding to the refractive index of core and optical fiber. Okay, so here the cladding's refracting index will be lower, cores will be higher. Okay, this is n1, it should be lower, this is n2, it should be higher. Okay, in our case we have considered n2 as cladding and n1 as core, but you get the point. Okay, cladding should be lower, core should be higher, and this is the formula: n1 as n2 by n1, refractive index of fractional index change. Next we have refractive index profile. Okay, so the curve which represents the variation of refractive index when it moves from radially outwards from the fiber is called as refractive index profile. So suppose that there is a medium which is having a varied amount of refractive index, means it is varying. Either it is becoming more or it is becoming less. So when light travels from here, its refractive index keep on changing. So in which curve it is changing, that is called as refractive index profile. Okay. So a third topic, which is the classification of optical fibers. There are three types of optical fibers. Single mode fiber. Okay, so as you can see, the dimensions present here, and this is the core, this is the cladding, and this is the geometry for the single mode fiber. Here only one light ray can be transferred. The cladding part is more here, and the curve is very small here, and the refractive index profile will look like this. Like this, it will go here and it will come back. Okay, so this is single mode fiber. The second one we have is the step index multi-mode fiber. Okay, what is step index? Step index will have a greater core and a smaller cladding. So here multiple rays can be transferred. Okay, so this is the dimensions given here. Can go through it, and the refractive index profile will look like this. It will be higher at this point at the top. Next we have graded index multimode fiber. Okay, what is graded? Graded, it is varying. Okay, here we will be having a different kind of means changing refractive index. Okay, it is not constant all the places, so that's why the path of ray will also become curved. Okay, so when there is a change, the path will also change, right? So it is a uniform change. Okay, slowly it is changing, so the path will also change in a curve form. Okay, so this is how you will be making the diagram for graded index multimode fiber. Here multiple rays are transferring and it is a curved one. Okay, so that's all, nothing more than this you have to remember in the types of optical fibers. Then we have attenuation. Okay, attenuation is the loss of optical power through the journey. Okay, so this is a very long journey and light will be going from here, it will be losing its power. So how does it lose its power? There are three main factors to which due to which it will lose its power. Okay, and this is the coefficient alpha, minus 10 by L log P out by P in, and it's expressed in decibels. So there are three reasons for it. Okay, what are those reasons? The first is the light absorption, second is scattering, and third is bending losses. Absorption means what? See, this is the place where the light hits. Okay, all the light is getting reflected, that we save for convenience, but some of them will get absorbed here. Okay, that's where it will lose its intensity. Second is scattering. Since it's passing through some medium, it gets scattered a bit here and there. Okay, that is the second loss. And third is the bending losses. So when the reflection happens, there is a bend present here. So if the bend is more or less, based on that, the microscopic or macroscopic losses happen. That is a very small level, but still considered a very long distances for miles, this will become considerable amount. Okay, so these are the three ways in which the losses have been a very important question from exam point of view. Okay, the last topic we have the applications of optical fiber. There are two applications present. The first is the optical fiber networking. Okay, what is that? The general, suppose that someone is in USA and they are producing some content, and we are able to watch it in the sitting in India. So there is optical fibers present here which are passing the information. Okay, so that is called as the passive optical network. Why it is passive? It is passive because it is not requiring any extra cost or any extra functions to perform. It's just a cable where the light is getting transmitted. So it is passive, and this is the optical network. You don't have to make this big diagram, just make a simple one here. Here we have the source, and here we have the receiver, and here we have the optical fiber in between. Okay, if you can remember more than this, you can do this as well, but this is a more simpler one. This will also do the same job. Okay, Next, we have the point-to-point optical fiber communication system. So this is a step-by-step process how the information gets transferred from the destination, from the source to the destination. Okay, so this is the message origin. Here the message gets generated. Modulator will remove the unwanted things from here, and carrier source will carry it and encode it into the proper format where it can be transferred either in the analog or digital. And channel coupler will transfer the information to information channel. This is the optical fiber present here, and from there it will go to the channel coupler. Channel coupler will again uh, remove the unwanted things present here and pass through the detector. This detector will detect the signals and it will change the code from the digital to the human readable format. The processing will happen, it will fine tune it, and the message output will come here. Okay, so this is another example, point to point. Okay, so this is all we have in the module 1. For the numerical part, I'll be uploading a separate video. So that's all for this video. And if you found this video helpful, if this video helped you, please like and share and subscribe. And thanks so much for watching this video. I'll see you in the next one.